everyone. My name is Luis Dominguez.
I'm Jared Martindale.
I'm Mohammed Naeem.
I'm Zahir Williams.
And I'm Shahidul Rahman, and we're JFK Robotics.
Now, before we go on about how we built our actual competition robot, we'd like to explain to you guys, or show you guys our first prototype of our concept robot. We built this robot because whenever we had an idea or a new solution to a problem, we wanted to try it out on this robot first, because we didn't want to just implement it on the competition robot where it might be difficult to switch things around. On our competition robot, it'd be different. As you can see in the video, our prototype looks very simple, but right here in front of you, you can see it's been through some evolution, because all we have done is just practice and change things around on this one so we can implement it on the first one. Something else that this robot helps us with is for our operators. Our operators get a chance to drive and practice while our mechanics are actually completing the competition robot, which provides an advantage for us.
Building our robot Vulcan, there were 4 steps to it. The chassis, wheels and driving systems, the arm, and the claw. The robot's specifications are in the menu. For the width, the lowest it's 14 and the highest is 16. And our robot has a 15 and 1/4 inches width. And for the length is 20 to 21, and our robot has a 20 and 1/8 inch length.
The restrictions for the height were 18 to 25 inches. Our height reached 24 and 5/8 inches. Previous years we used 2 gears. However, this year we used 3 gears, which resulted in a ratio of 1 to 2 to 4.
As you can see here, this is the blueprint of Vulcan. We developed this blueprint early on into the years. So basically, we input what we wanted for our height, width, and length restrictions to work on it. As you see, we use AutoCAD, and we decided it looks more efficient and best at showing a 3D model of Vulcan.
The chassis. In building the chassis, we needed a sturdy design so that it could support the weight of the arm as well as the claw.
We also knew we had to maximize our design. In saying that, I mean, we needed to use our space as efficiently as possible. We knew there was going to be multiple things implemented on top of our base, on top of our chassis, so we wanted to be able to use that space efficiently.
Also, we needed our structure to be balanced. We didn't want any weight too much on one side that would cause too much pressure on that one side, causing the robot to have unnecessary movements. And we also needed a firm resting area for the arm so that the Lego pieces, as you can see right here, if we didn't have this Tetris piece right here, the Lego pieces would have been going down too much and that could have caused damage. Problems with the chassis. Initially, the first problem we had were that the support bars for the frame were touching the gears. There were 2 bars on each side that were extremely close to the gears that caused the gears to crash against them. This would cause the wheels to be stationary. To solve this, we removed those support bars from the frame. However, this resulted in another problem. There was excessive flexing in the frame. And we solved this by adding the support bars to different areas of the robot, as you can see here and also over there.
Our next stage of building Vulcan was the wheels. We added omni wheels in the front for the robot to take sharp turns, and in order for the robot to move quickly and take sharp turns. And we also added large omni wheels on the back, as you can see here, for our robot to move faster and efficiently. We tried the hub tires before, but the friction of the gym floor was too much. That's why the robot wasn't able to turn left and right. That's why we went with the omni wheels for the best, to solve the problem.
Overall, the wheels lifted the robot approximately 4 inches off the ground. This prevented the robot from grazing or touching the ground, which would have caused damage. And we also added 3 gears to operate the wheels, as you can see right here.
The next reason for building Vulcan was the arm. While building the arm, we had the mindset to get at least 50 inches for the arm to reach up, because the conveyor belt which I'm doing, it needs the robot arm to go at least 45 inches. So we took 7 inches in count for our robot. Also, for the conveyor belt challenge, there is a 1 feet barrier that the robot arm has to reach over. that was in our mind while building the robot. Using this extending claw here, this extra frame, that gives us extra 12 inches. This is going to go over 1 foot barrier. Also, we wanted a lightweight arm because it's really hard to get the arm up because it's really heavy with the chain drive and everything. So we had this in mind and also have smooth mobility of the robot while building it. While building the robot, as I said before, one problem was the arm was way too heavy for the DC motor controllers to bring him up. So that when we solved it was, at first we had all the chain here around with 2 motors only. After that, the way we solved that is take some gear chains out, which made the robot lighter, and we directly got the motors and the chains together. So it was easier for the motors to pick the lift up and make it efficient for us for the conveyor belt challenge.
Along our process of building the arm, we faced another problem that came along. It was our height restrictions because, as he stated, we wanted our arm to reach at least 50 inches in the chest. With that, we had to apply height restrictions. With this, we added red and yellow reflective tapes to allow our spotter and also the driver to see how far can they move up so we don't lose the arm and fall and then lose the hand. Another problem was our aluminum tracks. As you can see, like at the beginning, they were very rough and rigid. So it didn't allow the robot to actually glide up the tracks to move properly for the lift. Our solution to solve that was we modified it. We got a nail filer, everything we made it smooth to allow the lift to move properly.
And lastly, another problem that I already stated was that arm was way too heavy for the gears to pick him up. So at first, we went with the regular gears, and it was not powerful enough to take it on. So then we had to change to worm gears. Worm gears which are much higher torque, and this is perfectly goes fine. If you guys want, I can show you the demonstration right now. It's perfectly lifting up and down, and because the amount of torque the worm gear has, it is easy for the motors to pick it up easily. The equation that we used to find the torque, the radius and the degree of the clever. That's using that, and the force using that we found out the amount of power we'll need to raise the arm up, and we divided by the weight, and we saw before we didn't think that it's gonna move up. That's when we changed from regular gears to worm gears.
I think we should show a demonstration of how the worm gears actually lift.
Yeah, you see, at first it was not able at all to pick it up, and after the 1 year, it's perfect.
During the next phase of building Vulcan was the claw. Now, since we already have a lot of weight coming from the arm, we decided we wanted the claw to be lightweight and flexible because we had to be able to do the conveyor belt and also pick up objects firmly. And we also wanted to be able since we flip to move back and forth from resting position to starting position to be effective. Now, after building this first problem, this picture actually demonstrates our first problem, where we wanted the object to crash firmly. At the beginning, our claw was not even able to hold the big ball that's presented there firmly. So to fix the problem, we added a cradle, which is presented here, to actually hold the balls firmly in any objects that's actually put inside the cradle.
Another problem that we had was the claw was unable to stay there. So we added a longer Lego axle in order for the axle to go into the NXT motor, and which prevented the claw from moving so much. And then another problem we had was the claw was unable to reach the ball over the 1 foot barrier. So we added one of the another taxi frame in order for the claw to reach over the ball and then get it and then drop it in its designated place.
Now for our final part was actually programming everything together. In programming, we programmed every single part of the robot in separate pieces, and then we implemented it all together at the end. The first thing we programmed was the drive motors. The drive motors was basically the same we kind of used as last year, so we implemented it onto our final product.
The next part of the robotic program was the autonomous program for the conveyor belt. This program needed the robot to exceed 3 feet and do a 360-degree rotation. In order to achieve this, we added extra time as well because we didn't want to risk the robot being stuck due to friction on the floor. And fulfill the autonomous part of the Conveyor Belt Challenge.
The next part that we programmed was our elevation system. We knew our elevation system was to require 4 DC motors. We knew we would need 2 motors on the outside for our lift, and 2 motors on the outside and 2 motors on the inside for our lift. So in programming that, we knew that we had to adjust so we can be able to control the speed and the power of which our lift goes up.
And lastly, we had to program the claw. For the claw, we used a DC motor in the first place to get the arm to flip, and a NXT motor for the opening and the closing of the claw.
This concludes our presentation. We will now be open for questions.
So how many students work on the entire project?
We have a team of 28 members.
Was that team broken up into smaller teams that work on different aspects of the program?
We kind of separate our team into, you would say, like military squads.
Okay.
So we have the Alpha Squad, the Bravo Squad, and the Charlie Squad. So most of those separate squads consist of 5 members, about 5 members, and that's how we separate our work on the robot. That way everybody can get a chance to work and we have simple rotation.
Do you know how much time you spent on the entire project?
34 minutes.
What is the breakup with freshmen and sophomores and juniors and seniors? Do you know that?
I mean, the way we run our team, it doesn't come like seniority with how old you are, or if you're a senior or a junior. We believe if you can work hard on the robot, if you know what you're doing, you know what you're talking about, then we can go right ahead and work. We need to know though that there's some members who have more experience, so we just consult with each other before actually making any changes on the robot.
Are there any freshmen in this group?
Yeah.
Which ones?
That's both of them are sophomores, and we're juniors.
Yeah, we're juniors.
Okay, so you got this.
Yes.
Because we always like to see continuity, you know.
I mean, our
This is-
team consists of more than 10 freshmen, and every new year we recruit 10, and most of them are freshmen.
Who's the CAD CAM person? Who did the CAD CAM drawings?
Oh, that's one of our other members outside on AutoCAD.
I mean, we took an engineering class here at PCC, and that's where we got the AutoCAD, and we learned it. So implementing that into this, we use that stuff.
That's it. Thank you guys.
Thank
you. Thank you.